Chapter 8, Part 3, Hydration Reactions. So, the first one that we're going to look at is acid-catalyzed hydration. Now, acid-catalyzed hydration of an alkene occurs in aqueous acid. So you might see it written out as it is here, as water and H+, or you could see an alkene plus hydronium. What you would normally see is something like 0.1 molar sulfuric acid, or you might see water and another acid such as phosphoric acid. Anything that indicates the presence of a reasonably strong acid and water is hinting towards acid-catalyzed hydration, as long as the acid does not create a nucleophile such as a halogen acid. So in this reaction, what you'll see is that the acid supplies a proton, which gets added to the less substituted carbon, and then you end up adding water to the more substituted carbon, which gives you overall a more substituted alcohol. This is an example of a Markovnikov addition. So let's take a look at the mechanism in detail. The alkene first starts off by attacking a proton. Since we are in aqueous acid, our source of proton is actually hydronium, because water would have picked up a proton from the acid. And then from there, we've added on a proton to the less substituted carbon. So we have the more substituted carbocation. And we also have an equivalent of water. So water is going to come along and attack the carbocation. And I'm going to stop drawing the proton that we added on a second ago because it is implied. It's on this carbon here. What is more important now is that we have an equivalent of water added to that central carbon and a positive charge on that oxygen. Another molecule of water can come along and deprotonate this, which gets us to our final product, although this reaction is in equilibrium. So in summary, the first step is to protonate the alkene, form the most stable carbocation. This might involve a rearrangement if necessary. Water then attacks the carbocation, which is a nucleophilic attack of an electrophile, and then you deprotonate to form the alcohol. So let's do a practice problem. We have sulfuric acid and methanol, switching it up just a little bit. Remember that methanol and water are very, very similar and they react in similar ways. Also, when it says catalytic acid, that just means a small amount, and that's really all you need. This is an acid-catalyzed reaction. So this is telling you that you have enough protons to protonate the alkene. So go ahead and pause and try to come up with the answer yourself, and then unpause and we can work through it together. Okay, so the first step of this is to first protonate the alkene. I'm just going to go ahead and draw a proton here. We don't need to draw out the structure of sulfuric acid for this. So the alkene is going to pick up a proton. So our question here is, which carbon do we want to protonate? Do we want to protonate the more substituted or the less substituted? Following Markovnikov's rule, we want to put the proton on the less substituted so that we end up with the more substituted carbocation. Now we know that the question that we always need to ask ourselves when we form a carbocation is is this the best carbocation that can be formed? I apologize, my cat sneezed and it distracted me. So is this the best carbocation that we can form? And if we look at this carbocation is secondary, and the ring that it's next to, first of all, has a tertiary carbon immediately next to it, and second of all, is a four-membered ring. Four-membered rings are not particularly stable. We are forcing carbons that would prefer to have a 109.5 degree bond angle to have something closer to a 90 degree bond angle. I believe it's around 88 degrees in cyclobutane. So our best move would be to do a ring expansion. This gives us a 5-membered ring with the methyl group sticking off of it. And now be really, really careful about where you put this carbocation. A lot of times we want to put it here, but that's not actually what's going to happen. So go through and number your carbons. That can help you out here. So 1, 2, 3, 4, 5. These are the carbons that will be involved in the ring. The methyl group is off carbon number 1, 2, 3, 4, 5. So it's carbon number 2 that actually lost electrons in this carbocation rearrangement. So carbon number 2 is where the positive charge ends up. So just be really careful with that. Make sure that you are actually thinking about it and not just defaulting to creating the most substituted carbocation, because that's not actually what happened there. Now, another mistake that students often make is they think, well, there's still a proton here. I could do a rearrangement. No, carbocation rearrangements cost a lot of energy, and we've already made a really significant difference by expanding to a 5-membered ring. So this is already better. But because of the cost of a carbocation rearrangement and how slow it is, another one just isn't going to occur. So at this point, the other species in our reaction mixture is methanol. Methanol is a lot like water. We have lone pairs on the oxygen, just like we do with water. So it's going to attack the carbocation. So this gives us oxygen with a methyl group and a proton sticking off of it. We also have a lone pair and a positive charge. Now, we don't want to leave that positive charge on that oxygen atom. Oxygen really, really does not enjoy that. Plus, that's not our product. So we're going to use another molecule of methanol to pick up that proton and deprotonate our oxygen. And this gives us our product, which is an ether. Really, really similar to the process of hydration. It's just instead of having another hydrogen on the oxygen, we have a methyl group. We also have another equivalent of the protonated methanol, which is what we also technically had in the beginning. If we had methanol and a catalytic amount of sulfuric acid, we haven't really done anything super crazy here. This is just going to be able to kick off another acid catalyzed hydration if we wanted to, if we had more alkene to react, which we probably would. Okay, so that's Markovnikov addition. We also have some other reactions. So our first one here is oxymercuration demercuration. This is still a Markovnikov hydration. It's still going to make the more substituted alcohol, but it does not have the possibility of rearrangement. There is no carbocation intermediate that forms here, and so you do not end up with carbocation rearrangement. So the conditions are here. And this isn't a particularly great example because no rearrangement would have happened in this acid catalyzed situation anyway, but it still would not do a rearrangement if that was a possibility. Here's a good example. We have this cyclopentene or methylcyclopentene reacting with aqueous acid. This would do a rearrangement to give us a 6-membered ring. And in the case of oxymercuration demercuration, you do not end up with a rearrangement. We also have hydroboration oxidation. This is our anti-Markovnikov hydration, and it also is a syn addition, which is important if you are going to do this with a cyclic alkene. So this is going to give us the least substituted alcohol. Now for both oxymercuration, demercuration, and hydroboration oxidation, I highly recommend making flashcards with the reagents on it. So put the reagents on one side and the name of the reaction on the other, and practice recognizing the reagents, and also practice looking at the name of the reaction and coming up with the reagents on your own. Now the mechanism for this is kind of interesting. This actually involves hydroboration as a first step. So the borane THF complex is reacted with the alkene. THF is just a cyclic ether that is a very common organic reaction solvent. So it's not really part of the reaction, it's just there. And what happens is the borane reacts with 3 equivalents of the alkene, and they all end up adding on to the end of the chain. You've also added on a hydrogen from borane in this situation. And then you do an oxidation using hydrogen peroxide and sodium hydroxide typically, and that's going to give you 3 equivalents of the alcohol through essentially a substitution. So the syn addition part is that if you do react with an alkene that is cyclic, the hydrogen and the alcohol from the reaction are added to the same face of the cyclic structure. So you'll have to represent that in stereochemistry if you have that situation. So in summary, we have 3 different types of hydrations of alkenes. We have an acid-catalyzed hydration, which is Markovnikov addition. The stereochemistry is not controlled. If there are chiral molecules possible, you will make enantiomers or enantiomers at that stereocenter. If there are other stereocenters, you would end up with diastereomers. The occurrence of rearrangements is quite frequent with acid-catalyzed hydration. With oxymercuration, demercuration, it's a Markovnikov addition still. The stereochemistry is not controlled, and the rearrangements are seldom, if at all. Hydroboration oxidation is anti-Markovnikov. You will make the least substituted alcohol, and this reaction actually is stereospecific. It goes through the syn addition of hydrogen and the OH group, and there are no rearrangements possible. Now you also have to be careful with this one. You can still have 2 syn enantiomers as your product that you would have to draw both of them for.